Hi, I'm Brad Bond with Richform Construction Supply. Welcome to the webinar. Richform's a dealer of concrete accessories in the province of British Columbia and Yukon. And one of the reasons we're putting on this seminar is when we've done lunch and learn sessions for engineers with Euclid chemicals. One of the most frequent questions is, do you have solutions for to extend the useful life of a bridge or a parking lot that isn't going to break the bank? So with that, we always talked about a little Euclid product called FLEXOLITH, and it's great for epoxy overlays on highways, and it's being used all through the US. We've got a lot of projects that we can describe to you. So I'm going to turn you over to Brian Salazar, who's the National Business Development Manager for Euclid in Toronto, and his partner, Steve Scarpinato, who's the Product Marketing Specialist in Kirkland, Illinois. So they give you both Canadian and U.S. perspective. If you want to ask questions, there's a spot on your screen to type them in, and I will relay them live as a moderator to Brian and Steve. And if there's too many questions rolling in, I will I'll hold them till the end, okay? You won't be identified by the questions. There's about 30 people participating. We got engineers, contractors, and the MOT from both BC and Yukon. So, Brian, with that introduction, over to you and Steve.
Great, thank you, Brad. I hope everyone can hear me well. I'm going to try and share my screen now, so you should be able to see the opening slide. Okay, the primary goal for today's presentation really is to talk about epoxy polymer concrete, or EPC. And really this system consists of two different components, the epoxy binder and an aggregate that goes along with it. Now each of these components can be tailored, of course, to adjust to the different conditions and different sites. The epoxy binder itself, there are things that we have to look at, like cure rates, which allows for good turnaround time for most applications. The modulus of elasticity of the material, which allows for flexibility, chemical resistance, acid resistance from vehicles, and adhesion is another big one, because these products can be used on concrete decks, it can be used on steel, it can be used on fiberglass reinforced plastic decks, aluminum. So we have to make sure that adhesion is a key goal of any of these products. Color is another issue. In some cases, aesthetics is important, so we can pigment these products as needed. On the aggregate side, we're looking for a texture, of course, in order to provide abrasion resistance, because we are talking about parking decks and bridge deck overlays. So durability is very important. The gradation of the aggregate is important. Sometimes color can play a factor as well, particularly if you're looking at a colored resin. It is a gap-rated material typically, so it's more of one size than anything else, typically in a number 8 category, if you would. These aggregates can be anything from the silica, sand, aluminum oxide, basalt aggregates, and there are others that can be used as well. Next slide, please. On the epoxy side, this little chemical chart here is just to show you what we have capability of doing with the epoxy and the amine chain modification. On the graph on the left side, it shows that we are able to manipulate these molecules suitably to accommodate the different modulus of elasticity that we're after. So the higher the higher the strength, the more rigid the resin. Obviously, that leads to a more high modulus material, which may not be suitable for exterior applications. And on the other end of the horizontal axis, there are elastomeric materials. The products like our FLEXOLITH fit somewhere in between into a low modulus category, which allows some flexibility but enough durability that we have good, stable resurfacing materials. Next slide. Boy, is that ever slow. So the FLEXOLITH is a product we're talking about, which is 100% solids, 2-component, low modulus, moisture insensitive epoxy binder. The moisture insensitivity is important here as well, because we can't always dry out these structures 100%. So we need something that does have some moisture intolerance, or moisture tolerance, I should say, so it has to be moisture insensitive. And it is formulated for low temperature applications, which allows us for either a quick turnaround time, or you can use it down into the 4 or 5 degrees Celsius range. Currently, the DOTs in the U.S., we have 27 states that do approve this product and is on the approved products list. We have 3 provinces, as well as some of the special provisions which do allow some localities to use this material, but it may not be in their day-to-day specifications, but has been used in numerous other locations as well. Next slide. As far as aggregate properties are concerned, this just gives you a quick rundown on what we're looking at. Again, they are gap-graded materials. They are fracture resistant, so they're very durable under vehicular traffic, with a typical mold hardness in the range of 6 to 7 or so. As you can see from the gradation below, 100% of the material typically passes the number 4 sieve size, and most of it passes the 30 to 75% passes the number 8, but very little else. So it's all in that number 8 size typically, which is the gap-graded, good gap-graded material. Next. This graph is showing some comparisons between the silica aggregate and basalt aggregate. That was a study that was run by the Strategic Highway Research Program a number of years ago, where they analyzed several hundred bridge decks with these overlays. The top of the graph, and we're sliding past it now, but the top of the graph, and essentially what I'm looking at is this graph on the right-hand side. Now, we've just skipped over that slide, but that's all right. The graph on the right side basically shows the wear resistance, oh, there we go, of the, that top line is the basalt number 8 grade material for bridges 3, 13, 19, and 23 out of the study, which shows under the bald tire skid resistance numbers, very stable numbers at around 48 or so, 45, 48 after the initial year, compared to the silica sands, which are typically down around the 20 mark. So the basalt seems to be a more aggressive aggregate, and it holds up a little bit better. Next slide. This study was conducted by Michael Sprinkle from the Virginia Transportation Research Council. And what they had done prior to 1990, they looked at 139 bridges, and they were looking at chloride resistance and skid resistance on these structures. And then from 1990 to 2000, they analyzed another 416 bridges. That graph on the right side, again, shows you the basalt number that I showed you previously, where the skid resistance number is maintained over a 25-year period, that 45 number roughly. And on the left graph, this one just indicates the chloride permeability. And it's showing a very low Coulomb rating of about 500 or so after 25 years, which is considered quite low. Anything below 1,000 is considered very low, and below 100 is considered negligible, which is where these products typically start out from years 1 to 4 or 5. Next slide. This project is just an example of the longevity of the FLEXOLITH material. This is the Grand River Bridge in Michigan, which was installed in 1976. This was already a 30 or 40-year-old structure that they were trying to preserve and get some extra life out of it. 30 years later, in 2006, this bridge was still being used, and then it was finally removed and replaced in 2008, 2009. This is a fairly high-traffic bridge. Back in 76, the traffic density was something in the range of 30,000 vehicles per day. So presumably it was considerably higher by the time they removed it. And with a salt application rate of about 5 tons per lane per year. So it was a good, real good test for this application, and this bridge held up extremely well over the 30-year period. Next. Okay, now the main benefits for using this type of thin film system, or thin overlay system, I should say, the main goal really is to reduce the dead load and really give you that running surface and durability that you're after. Now, these products are typically in the range of about 4 to 6 pounds per square foot, compared to that of asphalt or concrete in the 18 to 22 pounds per square foot. So obviously a big weight savings there, and some of these structures are old and may not be able to tolerate the added dead load. So only adding a 1/4 inch or so of material eliminates the need for any kind of approach issues and worrying about that dead load. The substrate protection, of course, it is resistant to dilute acids, as I mentioned earlier, gasoline, chlorides, low permeability, again, much less than 1,000 coulombs, and sometimes even less than 100 coulombs for the initial 4 or 5 years. Long-term skid resistance and wear resistance, as indicated by that SHRP study done a number of years ago, over a 25-year life cycle. So it does hold up extremely well from a skid resistance point of view as well. The low modulus material, being a low modulus product in the 130,000 psi range, again compared to concrete, which is much more rigid and stiff, no flexibility, in the 3 million to 6 million psi range. Rapid installation and turnaround is also another main benefit. These products can be turned around after the surface prep is completed and the material applied. You're back into business sometimes within a day or two after it's been installed. The ultimate goal, of course, is to extend the life of the deck. Next. Go. Again, typical applications. We're looking at bridge decks on the left-hand side and parking areas, particularly in the wear lanes and the turning radiuses where the tendency for more abrasion resistance or more abrasion is there. A lot of these membrane products, the flexible waterproofing membrane type materials, aren't as durable and they don't hold up as well. So we found FLEXOLITHs over the years have held up very, very well for this application. Next. There are a few steps involved in installing this system. The first, of course, being good substrate preparation, and this is key with any kind of surface applied material. We have to have a good, clean, non-contaminated, textured surface in which to bond. Ambient temperatures need to be somewhere plus 4 degrees Celsius and rising, hopefully. The epoxy resin is applied, the aggregate is broadcast into this wet resin, and then the excess aggregate is removed after the initial, anywhere from 5 hours to sometimes the next day when the epoxy is cured. Then a second application of the resin is applied, followed by another broadcast of the aggregate. And once that's done, the additional aggregate is removed 3 to 5 hours later, sometimes the next day as well, depending on the schedule. And you're back up in business, ready to go once that aggregate is removed. Next. Now, when it comes to surface preparation, again, this is quite often 90% of the job. You know, the products work well, they're well tested, but we have to make sure that we have proper surface preparation. Shot blasting is the method of preference for most applications. It's clean, it's self-contained, very low dust, so it is quite often the go-to repair surface preparation method. Abrasive blasting is also quite often used. Surface grinding, hydrodemolition, as you can see that unit on the bottom left. But the idea is to clean and remove all the grease, paint, oil, residue, any kind of contaminants that may be on that surface we need to remove, at the same time texturing it so we get proper adhesion. This next slide shows you the exposed aggregate after surface preparation and cleaning, and what we're looking for here is a CSP, or concrete surface profile, according to the International Concrete Restoration Institute, of somewhere between 3 and 5. This gives us suitable texture and porosity to allow that epoxy to bond well to the concrete surface. Next. When it comes to applying the resin on the surface, there are many means by which this can be accomplished. Anything from simply mixing the part A and B in a bucket with a mixer blade. This is something for a small application, of course. On the left side, you'll see a plural component pump where the A and B components are stored individually. They're pumped through the hose and then met at the static mixer at the end, which then mixes the A and B components. On the top right, this is for a large-scale job where you have two large tote tanks with the A and B resins, again going through a pump and into a mechanical type mixing method in order to get this material on the surface. Next. There's the application with the plural component pump. So everything is, the A and B stay in the individual hoses until they meet at the static mixer right at the handle. This is pumped out onto the surface. Next. With the epoxy resin being applied, either by roller, once it's been dispensed onto the surface, it needs to be spread out by roller or by squeegee in order to get a consistent film thickness. Next. And this is a bridge deck. In fact, Steve might have a bit of elaboration on the details here. This was a fiberglass reinforced deck in Iowa done a number of years ago. Steve, any comments on this one?
Well, I think you really wanted to show on this slide that he's blowing the aggregate onto that deck, and there's many different ways of dispensing the aggregate. I think you have some slides coming up on that. But this deck was an experimental deck done in Iowa that is a fiberglass reinforced plastic deck. It's been down now for about 6 or 7 years. It's kind of a long-term study that's going on. There's several different bridges throughout the United States that have FRP and then the FLEXOLITH on them that they're monitoring as an alternative to a concrete deck. Of course, it's a lot lighter than a concrete deck, and there's not going to be any corrosion issue and things like that. So it's just one of the many different things the agencies are looking at long-term for solutions to bridge deck problems and bridge deck issues. That's it, Brian.
Thanks, Steve. Next slide. That aggregate broadcast, as Steve indicated, sandblast equipment is quite often used with a shovel or something like that to redirect the stream, or it can be done simply by hand, depending on the size of the job and the abilities of the crew installing the material. Next slide. Just gives you an overall indication. There's the aggregate, so you can get a good perspective of the size. And in both shots here, they're actually applying the aggregate by a hose from a sandblast type equipment, using a shovel to redirect it into the appropriate areas to get 100% saturation. Next. This was a job done back in 1988 in Winnipeg. This is the aggregate removal process, but this was a resurfacing done over a summer. FLEXOLITH was applied, aggregate being removed, and then a second coat of the resin would be applied after this.
Yeah, they're just sweeping up the loose aggregate with that sweep.
Correct. That's a process of removing the loose aggregate that does not adhere to the resin before the second application of resin is applied.
Right.
And the next one. Coming, there's a finished product, and I think Brad was just holding up a sample of this material, so you get a little close-up there of the actual texture. So as you can see, it's quite aggressive. You certainly wouldn't want to fall off your bicycle riding on this roadway. It would tear you to shreds, probably. It's pretty aggressive, but you need that skid resistance when you're dealing with a bridge overlay, when you've got thousands of vehicles traversing the bridge at any given time. Next. Now, the curing schedule quite often dictates the type of resin that we use for this sort of product. This temperature chart here is just to give you an indication that when we install this type of product at typical summer temperatures at, say, 23, 24 degrees Celsius in the middle of the chart, the viscosity of this product is in the range of about 10,000 centipoise. So it's a fairly viscous material. Goes down, I would say, thinner than honey, for sure. But this gives us a gel time where it starts to react of about 45 minutes, so adequate working time, with a cure time of about 5 hours. Now, if we were trying to do this in the spring or fall when the temperatures are down around 10 or maybe 12, 13 degrees Celsius, you can see that that increases the viscosity by 50% and makes it up around the 1,500 or 15,000 centipoise mark, extending the gel time. And of course, the cure time now is double from what it was at room temp, or say a warm room temperature. Conversely, if we're doing it in the middle of the summertime, very hot 30-degree, 35-degree days, we're going to have very short working time with it, and your turnaround time consequently will be faster. You'll be able to turn that deck over a little bit quicker because the reaction of the epoxy and resin and hardener will be that much faster. So cure time is something that's critical depending on the schedules and when you intend to open these lanes back up to traffic. Next. When we're dealing with cold weather applications, there are some considerations that we do have site meetings ahead of time in order to discuss these things so everybody knows exactly what's happening. We need to store the materials in a heated location, either a warehouse or in a heated trailer on site. So this is where we would be having this pre-pour meeting in order to make sure the appropriate equipment and storage is on site. We need to condition those epoxy resins to somewhere in that 20 to 24 degree range, keep it around room temperature to keep the viscosity as low as possible to take it easier to apply. This also aids in the curing, of course, as I just showed on the previous slide. Condition the aggregates as well. Having a nice warm deck and a warm resin and then putting down very ice cold stone on top of this material tends to draw the heat away from the epoxy, and that will retard the set. So we need to condition the aggregates, bit protected as well. Blankets or heaters are quite often used just to keep the whole site warm and keep everything under control conditions. And then once the resin is applied, of course, we want to apply the mix and apply it as quickly as possible and then get the aggregate on as quickly as possible as well. And we can open it up to traffic that much sooner. Next slide. Here's an example of protecting the site and the materials. This is a job that was done in Edmonton a number of years ago, where on the right side you can see it's been enclosed. There are a couple of shot blast machines in there, actually preparing the surface. Heaters at both ends, it's tarped in, everything's enclosed and warmed before the actual epoxy is mixed and applied on the surface. So this is the kind of protection and cold weather considerations we're talking about. Next slide. Next slide. This is a job that was recently done in Edmonton just last September on the Stony Plain Road Bridge. The sidewalk on both sides, you can see the bridge on the left-hand side and close up on the right. This picture was taken in December when I was there last. This is two sidewalks that were resurfaced in order to extend the life of the sidewalks on the bridge. Perfect application for this sort of product. Next. Now, this is an interesting job. Steve has quite a bit more detail on. Steve?
Yeah, this project was done in 1994. It's the Pittsburgh Bridge going over the one of the three rivers in Pittsburgh. This particular job is was talking about other substrates like FRP and aluminum. This particular deck is a galvanized deck. It's a concrete. It's a it's a grid deck, galvanized grid deck, and they use lightweight concrete to fill the grid. And then they applied the FLEXOLITH over the top of it. Again, the purpose of this was because they wanted a lighter dead load. By going with the galvanized, they had these corrosion issues. Going with the lightweight concrete lightened the load, and of course the quarter-inch of FLEXOLITH on top is a lightweight overlay. So this bridge has been in place since 1994, like I said, and it's unblemished. It's doing very well in a very high traffic area of Pittsburgh, Pennsylvania.
Thanks, Steve. Next slide. Just a few examples here of some of the potential applications. This is the Springfield Mall deck rehabilitation, where the FLEXOLITH was used as the wear surface. Next. Another example, the turning ramp you saw previously, that's from the Fox Chase Cancer Center in Pennsylvania, PA. So again, in an area where we get a lot of freeze-thaw conditions, a lot of movement of these decks, and this deck has held up extremely well, and particularly in the turning radius. Next. This is a case study of a project that's ongoing, in fact, in Virginia, the Monitor Merrimack Bridge. This was started 2 years ago. It was supposed to be a 2-year project. It is still ongoing, as I mentioned. It's an 8-mile-long bridge. We expect to install something in the range of 120,000 gallons of epoxy over be almost a 3-year period now when it's completed. There were 6 shot blast machines on this project for surface preparation, 2 tractor trailer loads of sand and epoxy materials. The work is done primarily at night and through the summer months, of course. Anywhere from about 600 to 1,000 linear feet of bridge surface being redone every night. And it was initially designed for a 2-year resurfacing, but with weather conditions and so on, it's dragged on. It was supposed to be completed last fall, but they do have a little bit of work left to do next spring once the weather starts to cooperate again. Typically a work crew of about 30 men on site, and the material costs fairly inexpensive at $1.50 per square foot or so. And this doesn't include your surface preparation and installation costs, but the material itself is reasonably inexpensive. And this was the 2-coat with sand type application. The expectations from the state of Virginia, well, is to extend the bridge wearability again for another 20 years or so. So they're trying to save money for the taxpayers by not having to remove or resurface that bridge in any major way. Next. And these are some shots of the actual installation process. In the middle of the frame there, you can see the static mixer with the yellowish wand applying the epoxy, and the other workers using squeegees to distribute it evenly along the surface. Next. There's the aggregate being applied, and this was the most economical and the most efficient way of doing it. We're using a sandblast type equipment with a large rubber hose, so they can then spread it out onto the surface of the deck. Next. Second application, after the initial application of the aggregate was applied, we would then brush off and sweep off the excess aggregate that did not stick. The second application of the epoxy resin FLEXOLITH would be applied. Next. And the other major application that we use this material for, particularly in bridge applications, is for joints. The FLEXOLITH material can be mixed with the aggregate to form a mortar. That mortar can then be used to rebuild nosings, joints, headers, that sort of thing. This is a particular project on I-5 in Seattle, Washington. It was done 2 years ago, where they were actually rebuilding the joints. So it can be used as a mortar as well. And again, because of its low temperature capabilities, it can be used spring and fall. The materials are kept at a reasonable temperature. The set times are fairly good, so you can use it down to lower temperatures, again, with appropriate protection. So for something like this, you could isolate the joints, protect them, heat them, and actually do work well into the fall months. Next. This is just a copy of the technical data sheet that you'll find on our website. Go to euclidchemical.com and you will see the website a little bit later on. This is the technical data sheet that gives you all the applications, the things that we talked about, the compressive strengths, bond strengths, set times, etc. Sorry, you need to go back here, no worries. And that's basically what we had for you. Again, thank you for participating in this first attempt, and although a little bit sketchy on the actual technology, we are concrete people, not technology people, so we are doing our best to muddle through, but I think we got the message across. Listed there, you'll find Glenn Best, who's a sales manager at Richform, who you can contact, and our local sales rep, John Raymond, in Vancouver area. So anybody who has additional questions, you can certainly contact these gentlemen. They'd be more than happy to help you. At this time, if we do have any questions, Brad will gladly relay them on to us, and between Steve and I, we'll do our best to answer them for you. Brad, anything at all?
Would we lose our moderator?
I wonder. Well.
Yes.
There you are.
Yeah, we'll hold on a few seconds to see if anybody's got questions, but we'd like to let you know that we will repost this on the web in the next couple of days, so that if you want to visit it once again or share it with your teams, it'll be available to you, and we'll email you to notify you of this transaction. We'll also let you know that you can access Brian Salazar as well for technical questions, and we'll send you his email address as well.
Do we have any questions, Steve? Or,
okay.
Brad?
No, so it appears like we don't have any questions, so we'll sign out for now. If you have questions later, you got the contacts, and if you want us to send you a copy of the PowerPoint, let me know by email as well. I'm at brad@richform.ca or Glenn, double N, at richform.ca, and we can send you a copy of the PowerPoint presentation. Thank you for attending. Over and out. Bye-bye.